Tutorial, we're going to be going over the same program that we went through in the first two tutorials where we talked about how to write a C program using MIPS assembly. So if you haven't looked at those videos, it would be a good idea to watch them, but it's not really necessary. So let me just show you the program that we're going to be working with. So I already wrote the program, and just to be clear, right now I'm using a different operating system. This is Ubuntu, and we're going to be using GDB, which is the GNU debugger. You can use any operating system that you can install GDB on. I'm using Ubuntu because it's already installed, so it's pretty easy to do, and Ubuntu is free, so definitely it's an easy thing to use. So to begin, I have created a file, and let's see, where is the file? Okay, it's in recent. It's called cmp.c. And if you want to create this file in Ubuntu, all you do is you go to text editor and you just type whatever you want. So I've created it in here, cmp.c. And what it does is we just create 5 local variables in the main. I just put whatever numbers I felt like. And then we see if I is equal to j, then f is going to be g plus h. Otherwise, f is going to be g minus h. So we can see in this one that I and j are not going to be equal. So this is the statement that should execute. So once we've written this code, what we're going to do is just save it, and then we don't really need to look at it again. So what we do is go here. This is where you can search for everything, and you're just going to open up your terminal. So if you're not familiar with the terminal, it's the same for Mac and Linux. There's a bunch of different commands you need to know to use it. So when I type ls, you can see that we're in the home directory, and that's the directory where I saved the file. So you can see cmp.c. So that is the file that I wrote, and that's the one we're going to be using. So to use GDB, what we're going to do is we're going to compile it in a special way. We're going to type in cc-g and the name of our program. So we push enter, and we push ls again to see what's in there. Now we have something called out, and that's going to be the assembly of our program so that we can debug it, we can jump into different parts of it. So to begin using GDB, we type in GDB and then out, and then we hit enter. So now we're in GDB, and what we're going to do to start is we're going to put a breakpoint in our code because we want to be able to stop the code to stop. Once we run it, we want it to stop immediately so we can look through each line and see what's going on. So I'm going to type in break main, and that's the main function, but you can type in a line number or whatever. So I type in main, and then it says breakpoint at this number right here, and that's the line of our file. So then I'm going to type in run, and we started running the program, but it stopped right at the main because we put a breakpoint there. So now what we can do is we can actually look at our program with the assembly instructions in between the lines so that we can learn what's the assembly corresponding to the line of C code. So I'm going to type in dis assemble, and then I type in /m, and when I do that I get to see the code that I've written, and then right beneath it I see the assembly code. So what we're doing here, now this is just a basic procedure at the beginning of every function. We're going to be saving the base pointer, and to save the base pointer we're going to be pushing it to the stack, and then we're going to be moving what's the value of the stack pointer to the base pointer. So now the stack pointer is going to be at where the stack is, and the base pointer is going to be the same place because we've created essentially a new stack frame, and the base pointer has to be at the bottom because that's where the stack pointer currently is. So then what we're going to do is we're going to be creating all these variables, right? So when we're creating these variables, we're going to be moving these. This is move else. So these instructions are a little bit different from MIPS, but again, if you could understand MIPS, you can understand this because they're pretty similar. You just have to know a little bit the different syntax. So what we're doing is we're actually going from this way to this way. So it's a little bit different, and we only have to use 2 or 1 register depending on what we're doing. But we're just taking the number 0, because remember f is equal to 0. This is the number 0, and we're putting it at an offset -1,4 from the base pointer. So remember that the base pointer is going to have the highest address. So when we're going to smaller addresses, that's higher on the stack, right? So since the stack and the base are the same position, we can look at it as the stack or the base. It doesn't really make a difference. So we're putting the number 1 at this position on the base pointer, we're putting the number 5 at this position on the base pointer, 4 at this position, and 3 at this position. So it's like zeros on the top, 1, 5, 4, 3. So that's the stack pretty much. So then we have the code for if I is equal to j. So what we're going to be doing is we're going to be moving what's it at 8, which we could see is the number I, to EAX, which is just a register, and we're going to be comparing what's at 4 RBP. So what's at 4 of RBP is 3, so we're going to be comparing what's at EAX, which we said is 4, to j is equal to 3, so we're comparing 3 to 4. And if they're not equal, we're going to jump to this instruction right here, and it also says main plus 60. So that would skip all of this and go all the way down to here. Now one thing you might notice is that different from MIPS is that every instruction might have a different length. So you see this right here is 1 byte, is the difference between here and here is 1 byte. The difference between here is 3. This is 7, 7, 7. So the difference between the bytes is different. So each instruction is a different length. So anyway, because we said that we know they're not equal, we're going to be skipping this part right here, and we'll just go down to the other part because that's what's going to happen. But we can see they're pretty much similar ideas. If we were to go to this, remember we would do all the operations and then we would jump to an instruction at the end, right? We would want to make sure we skip over this. So our F is going to be, so first we're going to be moving what's at C to EAX, right? So that is that's H, and then we're going to be moving it what's at 10 to EDX, so that's G, and then we're going to be subtracting what's in EAX to what's in EDX. So remember, we put G in here and then H in here, so we're subtracting H from G. So we subtract H from G, and then we're going to move the result from EDX to EX again. So it seems a little bit confusing. Why would they do that? I think it's because EAX is the register that is more used for this type of operations. But I can't be sure because again, I didn't write this code. This is the code that the computer wrote. So now EAX has the result, EDX has the result, but we're using EAX. So we're putting the value from EAX into this minus 14 RBP, which is where F is. So then F is going to have the new value after this instruction executes. And then finally we're going to pop RBP, so we're going to get the value that we had from there originally, and then we're going to return. So now let's actually look at some of the different things that we can observe while the program's running. So the program is running still. We just executed one line. So if we type in print x and RIP, we can see that this is the next instruction that the instruction pointer, RIP's instruction pointer, is going to execute. So let's look at 4004F1. So that is all the way over here. So this is the next one that's going to be executed. So what we're going to let's take a look at the stack, right? Let's look at the stack. So this is minus 14 from the base pointer. So what we're going to do is we're going to type in x32b, and that's going to show us 32 bytes of of wherever we want to look at, and we're going to type RBP, which is the base pointer, and we're going to subtract 1 4, because remember 1 4, that's in hex, so that's 16 plus 4, so that's 20. So then we can see right here that this is where we would have our value for F. So let's do one. We're going to type an N to go to the next instruction, because remember, we've put a breakpoint, so now we can go through every single instruction. So we type an N, and then we can see that RIP is going to be F8, right? So we've executed this instruction. So now we are going to execute this instruction next. So let's take a look at what's in these 4 bytes for the base pointer. So we notice that this is the same because we just put the number 0. So let's do the next instruction. And then, so the next instruction, remember, this is going to be what we're going to do afterwards, because this is our code. So what we've just done is we've put G is equal to 1. So if it's confusing, just remember that we haven't yet executed this. So because we haven't executed this, the last thing we executed was this. So we put 1, and remember where we put it, we're going to put it at -1 0. So these are 1 2 3 4 are -1 4. So -1 0 will be these 4 right here. So let us see what's in them now. So notice that we have the number 1 in these 4. So this is going to be a little bit weird for you to look at, because if we think about it, we have 4 bytes here, but the leading number, this is 1 0, so this is going to be much, much bigger than 1. But we have to realize that we're reading this backwards. So this is called little endian notation. So we actually have to take this bit, this pair of bits, put it in the front. This is the second, this is the third, and this is the fourth. So really the 0 1 is at the very end. It's a little bit tricky to understand, but you get used to it. So let's go to the next one. So we've put 5 now, so then we can see that we got our 5 right here. Okay? So we could see that this is kind of what would happen as we move through the program. We're going to be storing all these in the stack. Some other things that we could look at that are sort of interesting. We can see all the bytes of the program. So our program is 75 bytes, and we're going to look at from the main. So we're going to see actually, because all of these are instructions in memory. Remember, these are the instructions. These are the memory addresses that have the instructions. So I type this, we're going to see all of the different instructions that are going on inside the program. If, for instance, we go to this address right here, 4004ED, let's go back to this, we see push RBP. So that is going to be the first one. So we can know now that push is this because it's only 1 byte. And then if we continue, if we look at the next one, move RSP to RBP, that's 4 minus 1, that's 3. So this is 4EE. We see that it's going to be these 3 are going to be those instructions. So we can actually see that the assembly instructions are translated into these things called machine instructions, and then that could easily be translated into machine code. So and machine code is just binary. So these can easily just be mapped into binary real easily. So we can actually reverse engineer a program, and we can figure out what's from the binary. We can turn it into hexadecimal, and then we can figure out what are the actual instructions that are being executed, and from there we can actually learn what's the program that's written. So it's possible to reverse engineer a program if you have the binary. So that's pretty cool.